an equation in two variables, such as y squared equals 2x or y equals 3x squared plus 2x plus 1, gives us a relationship between two quantities. And not every pair x and y satisfy these equations, and a point xy which does satisfy the equations gives us a point on the graph of the equation. So we say this point satisfies the equation if it makes the equation true when we substitute the value of x and y into the equation. For example, the point 8, 4 satisfies the equation y squared equals 2x because when I set y equal to 4 and x equal to 8 in the equation, it makes the equation true. Two other points which satisfy this equation are when I set x equal to 1 and y equal to the square root of 2. And you can check that this satisfies the equation. With y equal to the square root of 2, I get y squared is 2. And with x equal to 1, I get 2x equals 2, and those two numbers are equal. So I get a point which satisfies the equation. Similarly, if I let x equal to 2 and y equal to 2, I get y squared is 4 and 2x is 4, so this point satisfies the equation. A point which doesn't satisfy the equation might be minus 1, minus 1. If I let x equal to minus 1 and y equal to minus 1, and I pop these into the equation, I get minus 1 squared equals 2 times minus 1, and of course this isn't true. Minus 2 is not equal to 1, so this is not true. This does not satisfy the equation. So this point does not satisfy y squared equals 2x. The graph of an equation is the set of all points x and y in the Cartesian plane which satisfy the equation. And so we're going to sketch some graphs by plotting points, and this will allow us to see general trends in the graph, and we'll connect the dots to get a picture or an idea of what's going on in the graph. Later on in these lectures and in calculus, we'll discuss graphing in more detail. And in particular, in calculus, we'll talk about limits, continuity, and derivatives. And that'll give us a more complete picture of what the graphs look like. In particular, where they're going as x tends to infinity, whether they turn, concavity, convexity we can tell about using derivatives, and continuity if the graph has any breaks or not. So you have all of that to look forward to in Calculus 1, but for now we're just going to plot a few points and join the dots to get a rough sketch of the graph. So suppose I want to sketch the graph of this equation y equals 3x squared plus 2x plus 1. I'm going to make a table which gives me some points on the graph. And I'm lucky here because I have an equation for y in terms of x. So if I pick any x value, the y value on the graph is determined because y equals 3x squared plus 2x plus 1 is the unique y which corresponds to that x on the graph. So I pick a few values for x. I'm going to take minus 2, minus 1, 0, 1, and 2. And that'll give me 5 points in the graph, and it'll give me a rough idea of what's happening with the graph around 0, around x equals 0. So when I pick x equal to minus 2, in order for the equation to be true, y has to equal 3x squared plus 2x plus 1. So y must be equal to 3 times minus 2 squared plus 2 times minus 2 plus 1, which is 9. And so the point minus 2, 9 is on the graph. It satisfies the equation and it's on the graph. So I can plot that point. I have the point negative 2, 9 here. I've plotted. It's right here. If I take x equal to minus 1, then y is given by this formula, and y must be 2, so the point minus 1, 2 is on the graph. So I plot that point. If I take x equal to 0, all of these x terms disappear, and I get y is equal to 1, so the point 0, 1 is on the graph. And of course that's on the y-axis. If I take x equal to 1, then y is equal to 3 times 1 squared plus 2 times 1 plus 1, that's 6, so the point 1, 6 is on the graph. And if I take x equal to 2, I get y is 17, so the point 2, 17 is on the graph. Now this gives me a discrete set of points, but I can see general trends if I assume that this graph follows a trend. I join these dots, and it gives me some idea of how the graph is behaving around 0. Now the limitations of this technique, I've actually drawn the graph here, so we do get a pretty good picture of how this graph is behaving around 0. This is what I get when I join the dots, and this is the actual graph from a computer program, from Mathematica, the red line here. So I get a reasonable picture of what the graph is doing around 0 here by plotting a few points. The limitations of this join the dots method are that we're left with several questions. Does this graph continue to increase as we move to the right, or does it maybe turn around? And this is a question we can answer later with techniques from calculus using limits. So we need limits. And I might equally well ask this question: as the graph moves to the left, does it ever turn? And so we'll use limits and derivatives to answer this particular question. Does the graph ever cross the x-axis? Well, we can actually solve this, and we will solve it by solving an equation. So this graph would cross the x-axis if y were equal to 0. But we have a complete description of y in terms of x, so if we set this equal to 0, we can figure out where this graph crosses the x-axis. And the last nagging question is, what happens to the y values on the graph as x gets very large? And again, we need limits for this. So this will occur later in calculus. And probably this is more of a derivative question, number 1, than a limit question. Okay, so we're going to concentrate on the join the dots method to get a picture of a few well-known graphs, and we're going to use those graphs later, build on a catalog of graphs using graphing techniques to find the graphs of parabolas and so on. And we're going to try to answer this question for a few graphs later in this lecture.